Look at the roof line of this building. The structure forms a composite of jagged edges and intersecting planes. To calculate the exact material requirements for the site, an architect breaks the total footprint down into measurable polygons, specifically interlocking pentagons and triangles. This introduces the core focus of Section 8.2, the measurement of perimeter and area in polygons. At its most basic level, the perimeter of any polygon is the sum of the lengths of all its sides. We use specific formulas to standardize these calculations. Table 8.1 summarizes these for various triangle types, ranging from equilateral to scalene. Table 8.2 extends this to four-sided shapes, providing the perimeter formulas for specific quadrilaterals like rectangles and rhombuses. These tables are efficient for standard shapes, but the underlying concept of a boundary allows us to measure polygons that don't fit a specific template. As we move from theory to application, we will see how deductive reasoning allows us to calculate these boundaries even when the raw data provided is incomplete. In example 1a, we start with a triangle where every side length is known, 5, 6, and 7 inches. Finding the perimeter is a simple additive process. 5 plus 6 plus 7 yields a total outer boundary of 18 inches. Example 1b presents a more common challenge, side lengths that are missing entirely, requiring us to deduce them before we can find the sum. Here we have an isosceles triangle with a known base of 6 centimeters, but the two matching adjacent sides are unknown variables, which we'll call x. We find x by dropping an altitude line to point D. This line intersects the base at a right angle and bisects the 6 centimeter segment into two equal parts of 3. This creates two right triangles. We can now focus on just one, where x serves as the hypotenuse. The problem provides an altitude length of 8 centimeters for AD. We now have two legs of a right triangle, 8 and 3. By applying the Pythagorean theorem, squaring 8 and 3, we find the value of x squared, giving us the length of that unknown external side. Once x is known, the final perimeter is the sum of those two matching sides, plus the original base of 6. This demonstrates that when we lack direct measurements of a boundary, we can use the internal relationships of the shape to verify the data. Once the outer boundary is established, we can use those edge measurements to calculate the internal surface space, or area. Standard area formulas usually require a known vertical height, but Heron's formula allows us to find the area using nothing but the side lengths. Theorem 8.2.1 is known as Heron's formula. Before using the main equation, we must calculate a specific variable, the semiperimeter. The semiperimeter, noted as S, is exactly 1/2 of the triangle's total perimeter. This value becomes the core of the area equation, the square root of the semiperimeter multiplied by its difference with each of the 3 side lengths. The mechanics of the equation measure how the halved boundary relates to each individual edge of the triangle. This is an essential tool for scaling triangles, where finding a vertical altitude for a standard area calculation is often difficult. By utilizing Heron's formula, we extract a measurement of two-dimensional space directly from one-dimensional boundary data. To see this in practice, we'll use a triangle with side lengths of 4, 13, and 15 units. First, we find the semiperimeter. Summing the sides gives us 32, and dividing by 2 gives us an S value of 16. Now we substitute the semiperimeter and the 3 side lengths into the formula. We solve the subtractions within the parentheses first, comparing the semiperimeter to each outer edge. This leaves us with 4 factors to multiply under the square root: 16, 12, 3, and 1. Their product is 576. Taking the square root of that number gives us a final area of exactly 24 square units. If we had used the standard formula, 1/2 base times height, the result would be identical, confirming that Heron's method is accurate. This method provides an exact result using nothing but the additive and subtractive properties of the triangle's boundaries. Triangles are the building blocks we use to calculate the area of more complex polygons. By identifying an internal diagonal, we can split a 4-sided shape into 2 triangles and apply Heron's formula to each. This logic also applies to a cyclic quadrilateral, a shape where all 4 vertices sit on the edge of a single circle. We label these sides A, B, C, and D to prepare for a boundary-based area calculation. For these shapes, we use Brahmagupta's formula, which extends Heron's semi-perimeter logic to four-sided systems. In both cases, the progression is the same. We measure the one-dimensional perimeter to deduce the two-dimensional space it contains. Returning to our architectural example, we can see how these formulas govern the design and structural limits of real-world buildings. Measuring a perimeter is not about memorizing a static table. It is about mastering the geometry of boundaries. When we can accurately measure the edges of a structure, we can calculate the exact space contained within it.